Okay, so it's a couple minutes after 12, so I think we can get started. Robert, whenever you're ready, could you kick us off, please?
I would be delighted. Our speaker today is Axel Seifert from the German Weather Service. Axel got his degree from KIT, the Karlsruhe Institute of Technology, in 2002. He went from there to be an ASP postdoc at NCAR. And following that, he joined the German Weather Service's research department in Offenbach in 2005. From 2011 to 2015, he was posted to the Max Planck Institute for Meteorology, where he ran a research group. He was my next door neighbor at that time. Axel was for a while the head of physics development at the German Weather Service, but he decided that he liked doing the work rather than managing the work. And so he's now a senior scientist. Things have not changed at all. Axel is one of the most thoughtful and deliberate people, scientists I've ever met. So I'm delighted to have him present today. Thank you.
Okay, thanks, Robert, for the very nice introduction. And I'm really happy to speak in this seminar series about my machine learning work on cloud representations for weather and climate models. So today I will speak about three parts. The first will be about machine learning for warm rain processes, with an older paper. Then similar work for ice phase and mixed phase clouds. And then following up on that, a little bit a different topic on online learning of cloud cover, which we did recently. And I hope I have time to explain this third part as well, because it's actually quite interesting. And at the end, of course, I will give a very short summary on conclusions and a bit of outlook. So first part, machine learning warm rain process. So just, you know a lot about machine learning already, but I just thought I get us started a little bit just by saying that the parameterization problem for atmospheric models, it's really the task to find a relation or nonlinear relation between resolved model variables or prognostic variables and some unresolved processes or variables that we cannot properly represent on a given grid. So we basically just search for a function that relates resolved variables to unresolved variables. And we do that by physical reasoning using measurements and also a lot of benchmark simulations. And then when you look what machine learning actually does in, for example, supervised learning, they have some features or predictors and some labels or outputs, and they just search for nonlinear relations between these features and labels. And they do that based on data. So it's very much the same problem, and we can rephrase our parameterization problem very much as a supervised machine learning problem if we have such data, and especially when we talk about simulations as benchmark, we actually have that. So it's really straightforward to try to do that, and it's actually very tempting. So actually during the first Corona lockdown, I thought I do that as a kind of a home office thing. And I went back to my PhD thesis when I looked at warm rain autoconversion and accretion, looking at this as a classical parameterization problem. And it is, in fact, a very classical problem where we're trying to describe how rain forms from cloud droplets. And usually we distinguish then cloud and raindrops by size. So we have these two categories. And we have these processes like autoconversion, where rain develops from cloud droplets, or accretion, where cloud droplets are collected by rain. And in a two-moment scheme, we also have the self-collection processes, which just change the number density of the drops in each category. So you can get benchmark simulations for that by solving this Smoluchowski equation or kinetic equation, which describes basically the underlying physics in terms of droplets or bin microphysics, size distributions in very detail. And I won't go into detail today, but just say that of course we can solve equations like that numerically. It's just very expensive. And for the interesting physics, for the interesting kernels, these functions k here, when they are sufficiently interesting, then we cannot solve this equation analytically. That's basically the problem, because this k is nonlinear, and then all this becomes very difficult to solve. But what we can do, we can write down these autoconversion and accretion and self-collection processes as integrals of these drop size distributions. More or less, we can really boil down this problem to either having size distributions from simulations or making assumptions about size distributions, and then you can calculate all these bulk process rates. And this has been done a lot in the last decades, either doing this analytically with assumed PDFs, or people have just tabulated the results and built up big lookup tables for their schemes. Or we have built regression models using kind of statistical approaches using such benchmark simulations. Just saying that, yes, applying machine learning to this is really nothing very new. It's just a different tool, a different workflow, a different way of building such a regression model. So what I've done in this work is that I used the superparticle method, a Monte Carlo approach, so the superdroplet method of Shima et al. To do my reference simulations, because that's a very nice numerical approach. I will tell you more detail about this later in the second part. And then the tricky part is to really design the simulations in such a way that they cover all, the whole parameter range, all possible values, that you explore the whole phase space, because machine learning is not very good at extrapolation, but it's really great in doing interpolation within a data set. And as I explained, then we can calculate all these bulk process rates and train a neural network or several to emulate or these process rates. And then, of course, we want to, in the end, solve this kind of a ordinary differential equation system that builds our parameterization for our weather or climate model. So going into a little bit more detail, I've used TensorFlow for this. A very simple approach, just with fully connected neural networks. Of course, you do the standard machine learning stuff that nowadays everybody probably should know in science already, that you separate in training, validation, and testing data. Because in this case, the data spans really many orders in magnitude. It's also very natural to do this log transform of the data. That also has been done previously in studies when people used power law fits basically for their regression models. That's more or less the same idea of using a log transform. Then, because for example, mass and number has very different values. So you do the standardization to have everything in some nice range of values. And then really the interesting part comes where you select your predictors, or you can actually test this by trial and error, which predictors are most useful to describe, for example, autoconversion. This is actually interesting because in this warm rain problem, and I go back here a little bit to my figure here, it's always been a discussion whether autoconversion is only a function of cloud variables, which makes a lot of sense when you look at such a picture, that the number or the autoconversion rate should only depend on the blue stuff, but not on the red stuff. But you can also argue that the cloud droplets are, in your two-moment scheme are only representative for the mean of the cloud droplets, but may not contain much information about these larger cloud droplets that are at this boundary to the raindrops. And maybe using a bit of raindrop information to get an idea what's happening near that boundary is actually useful. So that has been a discussion, or that's where some schemes differ, whether you use actually the rainwater information to parameterize autoconversion. So this table summarizes a bit the setup, what simulation I did to span this parameter range. So we have liquid water content, the mean radius of the cloud droplets. We have a shape parameter of the gamma distribution that initializes these cloud droplets. And then this n is just kind of an ensemble number, how many simulations I did for the same initial condition, basically. Because it's a Monte Carlo model, it will give you different results for each simulation. And then basically, that's what I want to say here is basically that in the end, I have about 100,000 data samples for each process rates. So that's an important number, because now we built this machine learning model, very simple, just here, input layer, two hidden layers, output layer, some activation function, can actually be anything. Here I used the tangent hyperbolicus, but it could also be sigmoid or relu or whatever. So the details don't matter here too much. This model has in the end 600 trainable parameters, so which is much less than the number of data samples we have. So overfitting is not a big issue. And then we come to the results for these different models using different predictors. And you can see that simpler models have a larger error. Here you see mean absolute error in blue and mean squared error in orange. So this bars should be small to have a good model. So including more predictors gives us a better model. And you can especially see that including this LR, the rainwater content, into the predictors for the autoconversion rates does actually improve the model. Whereas whether we use it directly as a rainwater content or in this form of a dimensionless timescale, as I used it in my analytic parameterization, doesn't make a big difference or a significant difference for the machine learning. Yeah, because the machine learning will, if it has enough training data, will find these nonlinear relations. So we don't have to really spend much thinking on how to do the input, but just on what is the input. And as a comparison, I have here simple or not so simple analytic parameterizations. So power law fit. This is Karutinov and Kogan. This was the parameterization I did during my thesis. 25 years ago, basically. And this is the same equations recalibrated on the new data set. And you can see that the machine learning scheme looks better in these scores than any classic parameterization. So that would be a success, and most of the data scientists would now be happy at this stage and say, oh, job done, we have a model. But that's not sufficient for parameterization. For parameterization, we want to perform or see how this performs in an ODE sense. That we'll see in a second. I just want to show this plot here. This is the so-called partial dependency plots, which shows you for each process rates the dependencies that the machine learning model has found. And here the blue one is kind of the best neural network, and the red one is the analytic parameterization for my thesis 25 years ago. And you can see that they match surprisingly well. So the dark blue lines are very similar, have similar dependencies as the parameterizations that I did kind of by hand. And those where you see no red lines, those are the dependencies that I neglected in the classic parameterization. And you can see there they are mostly flat, which tells you very little sensitivity, and it was okay to neglect those. So this basically confirms or shows also that there's a good agreement between this classic parameterization and the machine learning model, and it's not very different. It also shows you that machine learning is not necessarily a black box. We can really look into it and see what it's doing and what it has found. But as I said, we want to see how it performs in this kind of ODE sense. Can it really predict things in a time evolution? So we put all these process rates together and solve these ODEs. And again, we compare the classic parameterization or the old parameterization with the machine learning approach. So now the gray lines are the reference simulations. The red dashed line is again the analytic parameterization, and the bluish lines are the machine learning models. And what you see are time series of the rainwater content that develops from a cloud droplet distribution due to autoconversion, accretion, and this always warm rain formation. And you have here 4 different initial conditions with faster and slower rain formation. And you can see that my old parameterization is more or less spot on. Yeah, that's because it makes really use of some mathematical properties of these equations, and yeah, therefore it hits it quite well. Whereas the machine learning model is a reasonably good approximation, but it has some biases. So it's too slow for the fast solutions and too fast for the very slow solution. So this is in contrast to the machine learning model being better in the approximation of the process rates. So where does this come from? Why is now the machine learning model worse than the analytic parameterization? To understand that, I want to step back one step and ask, oh, what have we actually done? So which decisions have we made? So when we develop a machine learning based scheme, and that's basically true for any machine learning model or parameterization, so we select or design the training data. Should we use observations or simulations? And if we use simulations, what kind of simulations? How are they done in detail? And then the second important step is that we choose model equations. So here, for example, we decided to use a two-moment approach with these 2 categories. So that's a choice. And the machine learning model is then limited to this choice that we made in terms of equations. And only the third step is the specific machine learning architecture and how we do the training and the hyperparameters and so on. And all those are important. And if we make mistakes in one of the three steps, we get a poor performance. And I just also want to emphasize this is also the kind of the creative part. So this is where the actual science would come in and our own creativity, how we choose these things. So where's the mistake in this case? For this, we look at these time series again. So this is the time series that you've seen before, how the rainwater content develops in time. And we have seen that the blue line has this slight bias, is a bit too slow. And here are the actual process rates. So now the black ones, solid black is the autoconversion from the superdroplet model, and the dashed lines are the accretion. The blue line is the approximation from the machine learning scheme, and the red line is the analytic parameterization from 20 years ago. And you can see that the machine learning model really tries to approximate the black line, and it does that quite well. And the red solid line, doesn't really do that all that great or in such detail. But what's strange about this this plot here is that we don't have really a significant autoconversion rate or accretion rate at time 0. And that's kind of the difficult thing here to understand, or what makes this problem so challenging, that when you have a cloud droplet distribution that is quite narrow, then it's impossible in the first minutes to form rain at all. The distribution has to broaden first and develop larger cloud droplets by collision between cloud droplets. So in the beginning, there is no autoconversion rate, or it's actually 0. And therefore, we don't have training data in these first minutes, and the model doesn't really know what to do here. It just, in the end, puts in a very small value. And the red line overcomes that by having a larger autoconversion rate initially, which looks a bit wrong, but it overcomes this issue. And this issue is actually, it's even more severe here in this, but whatever. So I tried to explain to you why this problem is so difficult. And this is because the autoconversion rate is or can be 0 initially. And this is a problem, especially because we have restricted ourselves to this two-moment approach, which really cannot describe this very early stage, because there the broadening of the cloud droplet distribution would be in the skewness in the higher moments of this cloud droplet distribution. So the machine learning model has no real chance to do that properly. It has no training data at T0, and then it develops this bias. So how does this analytic parameterization do it, and why is it so spot on for the time evolution, although the process rates are incorrect? That is explained by something called dynamic similarity, which is a property of this Smoluchowski equation. And in the end, it's kind of calibrated to give the correct ODE solution. So it's not actually trying to match the process rates exactly, but it's calibrated to match the time evolution. And it does that so well because it makes use of this dynamic similarity. And if you want to understand this in more detail, I would refer you to the paper. But people have followed up on this in the last years, and you can see how they used all the different approaches what I described to overcome these mistakes. So similar to what I just described, you can little bit abandoned to match the process rates and directly train on ODE solutions. This has been done using some parameter estimation approach, or you can use a different machine learning technique and really analyze the time series and do this kind of multi-step training over a finite time to capture this ODE behavior kind of. Also, this has been done now. Yeah, and the third idea is really to abandon this kind of a little bit ill-posed two-category approach of cloud and rainwater and really go to a one-category approach and have more moments for the total drop distribution. And also this can be done. So you can see how people are trying to overcome these issues using all these different approaches that come from these limitations that these simple schemes have. Whatever, I think this old approach is still hard to beat when it's implemented correctly, and it's also very simple and efficient. So you can look this up, as I said, in the papers, or here in my GitLab project, we have all the codes for this warm rain stuff. And now also the MaxNow, which I will also explain in a second, which I use for the super droplet simulations, is also open source and available. So you can reproduce all that in detail if you want. So the second part, mixed phase. So now this gets a lot more complicated because now we have mixed phase with ice and rain and snow and graupel and hail, and all these many interactions and processes that make mixed phase clouds so complicated. But the point is that all these are not as difficult and as nonlinear as the autoconversion accretion warm rain problem. So this is just complicated and not complex in a nonlinear way, at least in some sense. So here it might be really efficient to use this machine learning approach. And my goal was to really see whether this is really a method to speed up the development process, because developing such a scheme with classic methods takes 5 to 10 or even more years. And with the machine learning approach, you have this workflow and you can do all that more or less automatically. So does this work? Some more motivation. So the current schemes often, for example, do not have a degree of rhyming. So rhyming is the conversion of snow to graupel when snow starts collecting liquid drops and they freeze on the ice particles, and then you get this graupel or sleet and hail in the end. And this is really difficult if you don't have this degree of rhyming as a model variable, basically. And therefore, people have shown that this leads to some deficiencies in our predictions of MCSs and in situations where we have rhymed snow and so on. So one way to overcome this was this P3 scheme of Humerison and Jason Milbrand and others, where they actually introduced these degree of rhyming, and that has also been done before, but in the P3 scheme was the first way it was really very successful. So the question here was, can we develop something like a P3-like scheme using a machine learning workflow? Just a second. So what I tried to do was an ML-based P3-like multimodal extension of my existing two-moment microphysics. I motivated ML-based and P3-like already. Multimodal, I mean, I still have multiple ice categories like cloud ice, snow, graupel, and hail, in contrast to the very first P3 scheme. But that makes it then also very complicated because you have all these interactions in multiple variables and so on. And I did that as an extension of my existing scheme in Icon. So I just replaced all the process rates from my existing two-moment scheme with this machine learning part, like taking the engine out of a car and replacing it with a new engine, but keeping the car. But yeah, to generate the training data, I've again used a superparticle model, but now, of course, with ice phase. This is what we call MaxSnow. It's a Lagrangian particle model, and it really makes use of this superparticle approach by having multiple variables on each superparticle. So for each superparticle, for example, we know the ice mass, the number of monomers, so how many ice crystals form an aggregate snowflake. We know the Rime mass and the Rime density for this individual particle, or during melting, we also have the liquid mass as a prognostic variable. So this is kind of the ideal model to then generate training data for a P3-like bulk model. But of course, it's very expensive. We need about 1,000 particles per grid point, or even more if we want to reduce the Monte Carlo noise. So you can do 3D simulations, but they're very expensive, and that was not the right approach to generate data for the machine learning. But first, again, what do we want to do? We want to build an ODE system with these 6 particle classes. So again, ice, snow, rimed snow, corporal rain, and all have a two-moment formulation, and all have, or at least the Rime classes have this Rime mass, Rime volume, and bulk liquid mass, as in the most advanced P3 schemes. So this makes 23 variables and more than 100 process rates. So a PhD student would need quite a few months or even years to parameterize all that. So the question is, can we learn that simply with this Python machinery based on the training data? But again, the creative process is how to generate the training data. Here I've simplified it to an basically a box model falling through a prescribed temperature and moisture profile with some kind of liquid layers. And that's then so simple or efficient that I can do 10,000s of simulations and really build up again this hypercube of parameters to sample the parameter space. After some time, I realized it's completely insufficient to have only parcels falling through the atmosphere. I also need some updraft parcels that kind of come from the surface and see the microphysics as it is happening in a convective updraft. So I had to design special updraft parcel simulations to represent the processes in convective cores. And just as a side note, if I would use real or more realistic simulations, they would have an imprint of the current climate, but these very idealized simulations don't have that. So that can be maybe seen as an advantage if you want to attack climate problems. Again, this is nothing really new. It's very similar to what people have done in the 90s and called them bin emulating schemes when they used lookup tables to do this instead of machine learning. So machine learning approach is again as simple as before. TensorFlow, fully connected neural nets, individual neural nets for each process. Again, log transformed, very small networks, and so on. For some processes, I borrowed an idea of Gettleman and co-workers that you do first a classifier that tells you whether this process is actually happening, and only then you do the regression. So that can be helpful, but I needed it in the end, I think only for one process. And then I store all the coefficients just in netcdf files. So this is an example how these data sets look like. So these are just these 1D simulations. You can see them, or it's basically a parcel falling down that gives you this one-dimensional profile. And the solid lines are the Monte Carlo model. The dotted lines are actually the ODE solution of using the bulk rates from the training data. So just to check whether my training data is correct. And the long dashed line is the result of the machine learning model now already in an ODE sense. So it's already testing whether the scheme as a whole performs well. And you can see here that it does. So it captures these transitions from cloud ice to snow to rime snow to rain in the melting zone and so on. So, and this is just one example. You can do this for thousands of profiles and they all look reasonably good. That's the same for the number densities. There you see a bit bigger differences, but still, I would say, acceptable. Then you implement this in Icon or in any other 3D model. And here I, again, made a very simple approach and just implemented this in Fortran. You just read in the parameters or the weights and biases from the neural net, and then you evaluate this in Fortran, so you don't need any complicated Python bridge or whatever. Yeah, to optimize this a little bit, because in the end, 50% of the runtime of the microphysics is actually spent in the neural nets. So that became already quite heavy computationally. And yeah, also being an expensive scheme with 23 variables, it's in the end more expensive than the classic standard two-moment scheme. But yeah, it's a more complex scheme. So this is a comparison of two idealized scoreline simulations now with a new machine learning-based mixed phase and a classic two-moment bulk mixed phase. They look very similar at first. The left one is actually the machine learning one. The right one is the classic bulk parameterization. Here a bit a broader stratiform region, which is good. And then you can look into more details and you can really find that the machine learning being having this P3 ideas with the rhyme fraction and so on is doing better for this score line. So it really does a good job, for example, in representing this convective core and the stratiform region here in this reflectivity, for example. It really has this separation of the extended stratiform region and the convective core. Here, for example, would be a small observation sketch where you also want to see this separation in these two regions. And then you can look into the details and it all looks really nice and as you would expect it. So the rhyme fraction is high in the convective core and then becomes smaller in the stratiform region. And it even, for example, has a wet growth region of hail. So this is, for example, the liquid water fraction of Graupel, and you can see in this convective core, you have really wet particles going up to 6-7 kilometer height. So this wet growth region, which to my knowledge, no bulk scheme can do, no other bulk scheme. So this would be the next test, but I think I go over that quite quickly. Then I put it into a 3D real case icon to see whether it can do well in a realistic setup. This is a score line case over Germany. Left is the observation, middle is the standard two moment, and the right one is the machine learning. And here you can see it's not doing so much better, the machine learning scheme. So in this case, we had this lack of stratiform region issue, and it was not fully resolved now in this 3D real case run by the machine learning. It's not so much better. And the problem here, I think, is especially grid spacing. The scroll line simulation, the idealized was at much higher resolution, and here we are at 2-kilometer grid spacing. And the machine learning model is not optimized for these coarser grids. But you could also say that maybe the deficiency of the simulation is simply not due to the microphysics. Maybe it's the dynamics, the boundary layer scheme, or whatever. I would also like to emphasize that this is a very bad forecast for ICON. Usually it's doing much better. So the summary of the P3-like scheme, basically I just wanted to show that it's possible that superparticle models can be used to generate the training data. We could, of course, do this better with kind of a mix of different simulations, I think, throwing in 2D or 3D simulations as well. And then the machine learning approach is actually very efficient in this workflow to put together this parameterization. So I think it's a viable approach. It has, in my opinion, two major issues. It's difficult to capture the resolution dependency that we have in actual 3D models. At least the simple approach that I did does not have this at all. And the other issue that I see is that the fine-tuning or calibration in the full model is also difficult for the machine learning. So often in the end, we do some tuning of our models, and in the machine learning part, you couldn't do much of that. I want to give you a short glimpse of what we are doing or have been doing on online learning, because that tries to overcome a little bit this problem of fine-tuning and calibration. So putting really a machine learning part into a full model and using data assimilation techniques to train it online or end-to-end, whatever you want to call it. And this is then, of course, a team effort where more or less other people have done the hard work, and I'm mostly presenting. Just a quick information that there are two different kind of models when it comes to cloud fraction and microphysics. Most climate models have a cloud scheme, then they calculate a cloud fraction, and then they calculate the microphysics on that cloud fraction, and this is passed then to the radiation. For example, IFS is doing it like that, ECMWF model, and as I said, most of the climate models. In ICON, we actually do it the other way around. We have only gridbox mean microphysics, and after that we do the cloud scheme that kind of puts in the additional subgrid clouds, and this is what we pass to the radiation. And the cloud scheme is, of course, then also informed by the boundary layer scheme and the convection scheme and so on. So this is really a central part of our model where all or many things come together and prepare the clouds for the radiation calculation. So that would be a really nice place to replace this by a machine learning method and then do this online learning. And this is what we tried to do. So we replace our existing cloud scheme by a machine learning emulator. And then we want to do a calibration or tuning of that by an online learning approach. And this is also motivated because here you could also put in aerosol, for example, and look whether aerosol cloud interaction would lead to a different cloud information. This is what I looked at in this context of this dusty cirrus phenomenon. So what we do is we have an atmospheric model, we do simulated observations, we compare them with real observation and trying to optimize the model for that. And to get to the observations, we use a forward model, in this case, Atitov, or especially the visible part, which is called emphasis. And this is already based on a machine learning approach. So this forward operator is now already a neural net. This is important because here we can do this differentiation or backpropagation that allows us to do this online learning. And as you can see, this connects our model state to a visible satellite image. Here would be another example. So this is the geostationary visible image, and this is the forward simulation from ICON. You can see it looks okay. It looks actually pretty good. It's 13-kilometer global model. It's a bit kind of milky over the oceans, so it has a bit too much cloud cover over oceans, and that's another motivation to do this. So what we do now, we have our prognostic variables. We do this cloud scheme. Then we have the cloud variables. We do this forward simulations, and we have this observations and simulated observations. Now we replace this cloud scheme by a neural network that we train. So this is the neural network, again, fully connected, small. We train offline at first, just with 300,000 columns. And yeah, that works. So we can do an emulator for this cloud scheme that we have. Here are some scores, bias and MSE. And the orange, the neural net, is actually better. So the emulator is better than the original scheme, which is a bit surprising. But I think it's because the emulator does a little bit smoother fields, and that's better in these kind of scores often. Okay, and now we have that, and now this part of the model basically can be fully differentiated, or we can do the back propagation from the observations to our neural network weights. So we can optimize this part using a loss function, and here this y are the observations. The H, capital H, is the forward operator. The X are the model variables, and this F and N is our cloud scheme neural network operator that has the prognostic variables and this neural network weights that we want to find and optimize. So we minimize that, and as an additional term, in each step, in each learning step, we want to keep the difference in the weights small, so we don't have to have big learning steps or big jumps, but only kind of incremental learning. That what we guarantee by having this additional terms to make the difference small. And here you can again see that this works, at least when we have this alpha, which is in front of the weights term. When we have the small, so a small learning rate, then the model is stable and starts to improve, or at least slightly or slowly. And we can also do this online. And again, we find a slight improvement in RMSE and a bigger improvement in bias in these observed variables, or in these, during this training. And then you can check how the profiles change here: cloud fraction, liquid water, and cloud ice. And you can see that, during the learning, it reduces a little bit the liquid clouds, and it puts in more ice clouds and so on. So we haven't validated yet, but it looks reasonable. Maybe a bit too much ice up here, but it's not completely unreasonable. When we do an independent check with serious broadband, then the improvement is actually not significant. It's again not making things much worse, but it's also not a great improvement. So that's what I wanted to show about this. So that was an interesting exercise. It was not so successful as we hoped, although it kind of works. And unfortunately now this project has ended, and unfortunately will also not be continued. I hope they will still write the paper, but we will not follow up on this. So I'm already at my summary and conclusion. So I've shown you that machine learning can indeed be used to develop microphysical parameterizations. These Monte Carlo superparticle models are very useful, in my opinion, to do this, and therefore we can spend some time developing them further. Important is really how to design this, and there I disagree with some of my parameterization physics colleagues who are really, who don't like the machine learning stuff so much, because I think that this is really interesting work. So designing these simulations, thinking about how to do them best, and choosing model equations and so on, is really interesting. The disadvantage is that tuning is difficult. Online learning may be a way to overcome that, but it can be difficult. Now comes more the outlook. At least at DWD, it's not clear whether this kind of hybrid modeling, where we mix physically based model with machine learning, will get more attention, because they would need it to overcome these issues. But now pretty much all resources go into this pure ML methods, where you emulate the whole model. And we just don't have the resources to do all different approaches at the same time. And people argue that the gain from these machine learning based parameterizations is actually small. And as I said, in my opinion, we would have to invest in these online things, online learning methods, to really make them useful. So that's all what I wanted to say today. And I'm happy to take your questions.
So from Divi Patel in the chat, what guided your choice of neural network architecture over other machine learning approaches like random forests or gradient boosting, which might offer more interpretability?
Yes, I actually tried random forests, and especially for this very first problem, also together with Stefan Raspi, also used or tried to beat the simple neural nets with other techniques, but the other approaches were not any better in terms of scores. The neural nets were actually pretty good. And yes, the random forests allow a bit easier interpretation sometimes. But as I tried to show, these partial dependencies plots also give you a lot of insights how the neural networks do the optimization and the regression. So we were actually quite happy with that. But it was a kind of informed choice. We tried other things as well.
Great, thank you. Robert, feel free to unmute and ask your question.
Hi, Axel. Thanks so much. I was struck at how well some of the older parameterizations did, and you hint a little bit at this in your last point on your summary and conclusions, that some of the advantages from the ML parameterizations are sort of marginal. And you explain a little bit why that is. I'm curious if there's some way to anticipate that result ahead of time. So when you do the end-to-end training, you have the ability to bring in unseen data, in your case in the form of series. I wonder, is there some way a priori to know whether some other approximation, be it analytic, be it some other regression model, is as good as you're going to get for that process rate?
Yeah, I don't think there's a way to know this a priori, whether you can beat or not beat an existing scheme. I think it's what drives a lot of our research, that we still think, oh, we can do better than that. And I think that's good that we are still trying to do that. But for example, for the convection schemes, people were not so successful in the last 2 decades. But I think it's really hard to know which parts of the model could still be improved, either with classic or with machine learning parameterizations. For example, I think that gravity wave parameterizations, gravity wave blocking, low-level blocking, those are parts of the model that haven't received so much attention. And maybe by using data-based models, that's a part where we could do something to capture, behavior in different regions or seasonality and things that are not included in our current scheme. So I still think that there is room for improvement, either by classic or machine learning based methods, but there's no low-hanging fruit. And a lot of people thought that, just by using data-based methods, they would get easily much better, but that hasn't shown up in the last years, I think.
Okay, great. We have time for one more very quick question. We have a 1 o'clock hard stop in this room, unfortunately. Any last questions or thoughts before we thank Axel again?
Maybe I would just ask you to point to any information that's available about AICon, which I wasn't aware of.
Oh, it's basically a similar approach like AFS, so this GraphCast approach that also Google did. And then in addition, we have our own reanalysis, fairly high resolution reanalysis from ICON, which is not covering so many years as ERA 5, but only a shorter period, but seems to have a good quality. So it's getting there, I would say. We are hoping to make it operational this year. So that would be a really big thing, to have a machine learning based model in parallel to our classic model, also for operations. And yes, we are investing quite some resources in that. But in some sense, it's still repeating what others did, but with our knowledge and experience in atmospheric science and forecasting, and I still hope we can do better in some parts than others. But it's getting close to become operational.
Thanks so much.
Hey, thank you so much again. And please join me, everybody, in thanking Axel again.